This is a question from February-March 2022, variant 42, question number 12 on astronomy and cosmology. Number 12A states what is meant by luminosity of a star. The luminosity of a star is defined as the total power radiation produced by a star. Then in part B, the luminosity of the sun is 3.83 times 10 to the power 26 watts. The distance between Earth and the sun is 1.51 times 10 minus 11 meter. Then you have to calculate the radiant flux density F of the sun at the Earth. Give a unit for your answer. So the formula to use is F equals to L divided by 4 pi d to the power square. You notice that L and D are given to you. So F can be calculated equals to 3.83 times 10 to the power 26 divided by 4 pi 1.51 times 10 by 11 square, which will give you 1340 watt per meter square. Then for units, the unit for L is watts, and then unit for D is in meter. So it's L is the unit for L would therefore the unit for F would therefore be watt per meter square. Then in part C, use the data from B to calculate the mass that's converted into energy every second in the sun. To do this question, you must use E equals mc squared, where m is the mass defect and E is the energy that's produced. You must know how the sun produces energy. The sun produces energy by nuclear fusion, where it changes the mass into energy. E is given to you, or rather E is 3.83 times 10 to the power 26. And then your C is the velocity of electromagnetic wave. So therefore, you can calculate your M, which will give you 4.26 times 10 to the power 9 kilogram. That means the sun is losing 4.26 times 10 to the power 9 kilogram every second. Then in part D, the radius of the sun is 6.96 times 10 to the power 8 meter. Show that the temperature on the surface of the sun is 5770 Kelvin. The equation to use is L equals to 4 pi, a constant, R to the power square, R square, then T to 4. You notice that in this question, R and L are given. Then your constant of proportionality is 5.67 times 10 minus 8 watts per meter. And then Kelvin minus 4. So you substitute the values into the equation, you can show that your temperature is 5770 Kelvin. For part E, the wavelength lambda max of light for which the maximum rate of emission occurs from the sun is given to you 5 times 10 to the power minus 7 meter. The temperature on the surface of the star Sirius is 9940 Kelvin. Then you have to use the information from D to determine the wavelength of light for which the maximum rate of emission occurs from Sirius. To do this question, first you draw the graph. The graph is this graph here. The graph is the graph of, the graph is a graph of rate of emission against wavelength. And then this green point and the red and the purple point represent the peak wavelength, lambda max. So to do this question, we need to use Weir displacement law, which states that lambda max is inversely proportional to temperature. Or you can also say lambda max times temperature in Kelvin is a constant. So you can set up two equations, equation 1 and equation 2. Equation 1 is for the sun. 5.00 times 10 minus 7 times 5770, which is a temperature we calculated in your part D, equals a constant. And then your lambda max for Sirius times 9940 equals to another constant. Then you equate equation 1 to equation number 2, which will give you 5.00 times 10 minus 7 times 5770 equals to lambda max times 9940. So lambda max for Sirius will be 2.90 times 10 minus 7 meter. And then this is a summary of the facts that you must know to solve this question. Number 1, you must understand the term luminosity and radiant flux density F. Number 2, you must understand the relationship between F and L, where F equals to L divided by 4 pi over 4 pi d squared, where d is the distance between F and L. Then number 3, you must understand how nuclear fusion produces the radiation energy in the star. And number 4, know the relationship between mass defect M and the energy E, where E was mc squared. Number 5, recall and use band displacement law, which says that lambda max is inversely proportional to temperature to predict the peak surface temperature of a star. Then number 6, recall the use of Stephan-Boltzmann law, where L equals to 4 pi, a constant of proportionality, R squared T4, where R is representing the stellar radii, temperature is the surface temperature of the star, and L is the luminosity of the star.